Hello, in this lesson, we're going to continue to talk about the proof of trig identities. I hope that when you're watching this program, and when you watch this lesson, please have your paper pencil with you and follow my steps, even though we cannot be together, interactively. But if you have any questions, and you should let me know. And also, after you watch the lesson, you will try to prove what's been done in the lesson all by yourself to see if you can do it. This is extremely necessary as a student to learn these skills, because sometimes you can see it's much easier. It seemed to be rather easy when some other people are doing it. But when it comes to your turn, it's not necessarily, but that's how you identify what you missed and what you need to compensate for your for that part that you could not do. Okay, so this is an effort you need to make consciously on your part. It's just watch and try and make those efforts until you can do everything by yourself. All right, so when you watch these examples we went through, and you can also think about that, did she cover everything? Did she cover every way? There are other ways, okay? So today we're gonna continue and on some more identity proofs. So you can see last time we picked some examples from the proving identity on the first set, right? We did some, exercises here. And the next one, I'm thinking of doing one of the identities in set 1, and then we pick a couple from set 2. You can see set 2 looks a bit harder than set 1. But as a matter of fact, if you get down to it, right, if you take your paper, pencil, and start to work on it, or if you want to write on your iPad, that's fine too. You just have to put your pencil to work. You have to put your pencil to work, whether it's virtual or not virtual on paper. It's a process you have to do, and no one can replace you. No one, absolutely no one can replace you. Okay, so with that understanding, so let's look at some examples. Okay, the next one I like to work with you would be number 10, set A, number 10. Number 10. Number 10, you're asked to prove tangent x plus cotangent x equals to secant and cosecant x. Oops, what did I do? Equals to. Okay, so this is a to be proved. Okay, proof. Once again, there's 3 formats. There's 3 formats. Okay, 3 logical formats. 3 logical formats. Okay, so never ever do 2 sides at the same time. Okay. I hope that you guys got that. So usually I always have a piece of scratch paper to scratch with me, okay? Because sometimes you just need that extra space, extra time to work it out before you write down the formal proof to show to your teacher or show to a professor or show it to your reader to make it as well presented as possible. Okay, so here there's no difference. So I'm gonna write think out aloud. Okay, you can start from the left, you can start from right, really, okay? But you can only start from one side at a time, or you you work on the left, will reach certain place, and you work on the right and reach certain place, and that certain place are the same. 3 formats, okay, 3 formats. So typically, it's more often than not is that you start from the side that looks a little bit more complicated, okay? So I start from the left. Okay, and then I would try to figure out, right? Because you have a tangent, and on the right side is secant, cosecant. So how am I going to make that connection? Okay, so you go from left, you're going to end up on the right. So here I'm going to have sine x, cosine x, right? Plus cosine x, excuse me, over sine x. Okay, and then what I'm going to do? Well, naturally, you would think of finding a common denominator, right? So finding common denominator looks like the common denominator is going to be, LCD, if you like to use that word, okay? And I just use the common denominator, okay? It's the sine x times cosine x, okay? So on the first term, I already have a cosine x. So I just need the sine x in the denominator. So I need sine x in the denominator to balance it off to justify the equal sign, right? So maybe I just write it this way, right? This is easier for me and it's easier for you to read. So I'm just going to multiply by 1. So this is going to be sine x. Right? I multiply by 1, anything times 1 stay the same, right? Principle number 1. And the next one, what's missing in the denominator is a cosine x. So I'm going to choose cosine x, right? And then I need to balance, make sure the equal sign is balanced. So I'm going to have cosine x on the top. Okay. Now, next step. So now we have the common denominator, and the top sine x to multiply sine x, that's sine square x. Sine square x. And the denominator is sine x multiply cosine x. Plus, okay, on the other side, on the other term, the second term, we have the same denominator. Oops, wait. We have the same denominator, which is sine x cosine x, and the numerator is a cosine square of x. Now we have the same denominator, and we're going to keep the same denominator and add the numerator. So we add a sine square x plus cosine square x. Okay. All right, so what's on the top? The top is 1, right? So because we have that identity, sine squared plus cosine squared equals to 1. So we have the same denominator. We have that until the end, and the top is equals to 1. And the bottom can be separated into 1 over sine x multiply 1 over, oops, 1 over cosine x. And of course, this is a cosecant and this is secant, right? So in the end, we got that equals to cosecant x multiply secant x. And that's the right-hand side. That's the right-hand side. Okay, that's the right-hand side. So in our steps, remember when you write down those steps, you are to present it to the reader and tell the reader, number one, you have these logical concept, right? And this is to be proved. So pretend it's not true yet. It's not true yet. So we start from one side and we ended up on the right. We start from the left, we ended up on the right. And then you have demonstrated that the left is indeed the same as right. And every step needs to be justified. Every single step needs to be justified. So you see from the think out loud we already got it. So now you can, for me, what I can do, I'm going to show you how to show work. How to show work, okay? Now, when you show work, of course, you're going to remove that. You're going to present it nicely. You're going to present it nicely. So tangent, so you start from the left, you tell the reader, you start from the left. I would typically line them up. Okay, this is what I would do. I would line them up nicely. Okay, I would line them up nicely like that. Okay, there are steps that can be trimmed. It's up to you. It's up to you. Okay, if you skip a couple steps, for example, if you skip this step, that should be fine. That would be fine. The reader usually can follow. Okay, if you skipped this step, for example, and that's fine too. Okay, because the reader can follow. But you must guarantee that every equal sign is justified. Every equal sign is justified. You can even skip this step, right? You can present this step and go straight to here. So there are multiple steps you could skip, but you have to make sure every equal sign is justified. Every equal sign is justified. Okay, that's very, very important. That's very, very important. Okay, and then you're gonna have a closure. Okay, you're gonna have a closure. Thus, right? The typical closure is very, very, very common, right? You just say, this is ask you to prove it, right? Now you have, so you just say, okay, thus this is true. So you're telling the reader, thus this is true. You can see you're telling the reader the left-hand side is the same as the right-hand side, okay? At the beginning, we don't know. At the beginning, it's telling you, can you show this left-hand side is the same as the right? Okay, that's what this question is about. So please do not do this. This is the second time I talk about this, okay? Do not do this. I see this too often. Okay? So the reader, the student will typically just do this. Okay, so let me present this faster, okay? I have a faster way to present this. Oops, whoopsie, sorry. Okay, the student would do this. Okay. In fact, the student does everything correctly almost, but the logic is wrong. Okay, so this is what the student do. The student would do that thing. Okay, don't do this. Okay. And remove that over here. Okay, with or without. Okay, and the next step, the student would do this. It basically did not do anything on the right-hand side. It's what's the problem is the logical structure. It's a logical structure. So I'm going to tell you how this kind of work is going to be read. Okay, how it's going to be read. Do not do this. I mean business. I mean business. When I see this kind of work, right, I'm going to tell you as a teacher how we read it. Okay. You're asked to prove. We are asked to prove. Okay, we're asked to prove, right? To prove this is true. And then you tell the reader, this is true, right? You tell the reader this is true. And then this is true. And then this is true. Then this is true. And then this is true. Then this is true. Then this is true. And this is true. If it is true, you don't need to do anything afterwards, logically speaking. So that it's the logic of the structure is wrong. So how many points usually are taken off? Half. Without that logical concept, logical understanding of this question, you present a work like this, you basically use what's to be proved as truth. We don't know if this is true yet. You already start using it, right? The student is already using it. We don't even know this is true and you're using it. So do not present this kind of work to any teacher, okay? Just do it either from left to right or right to left or left and right to the third place. Do one of the three structures. Never ever do this. You probably could do this, on your scratch paper, but never let this kind of work to be shown in front of anybody. Okay, just for yourself, if you have to do it, if for yourself, okay, with the understanding you're going to make the right logical structure. Okay, you can see when I was showing you the think out loud part, I don't even do that in think out aloud part. So as a principal, I recommend you never ever do this. Don't do this because logically it doesn't make sense. Well, it may make sense to you, but I'm a teacher, right? So I represent a group of people in the mathematical community to tell you what kind of work is acceptable, what kind of work is accepted as with lower points, and this is one of them. Okay, so please do take it very seriously because I see this kind of work repetitively. Okay. All right, I think that's enough. That's enough about what's to do and what's not to do. Okay, so let's take another. So this time I'm going to take a question from set B. Set B. Okay, set B, I'm going to take the first one. The reason I'm taking the first one, even though it's not a very difficult question, is because some of the formula, right? I'm going to take number one, number three, because some of the formula involved are very, very common, very commonly used. And where you learn those long time ago, okay? So 1 minus cosine x multiply 1 plus cosine x equals to 1 over cosecant squared of x. Okay, so let me make the fonts just a little bit larger. So this is to be proved. This is to be proved. Okay. Think out aloud. When we see this format, it should remind us of this form. It should remind us of this form. A minus B multiply A plus B. This formula, okay, you may find yourself still using this formula when you're taking calculus 3. And needless to say, you're going to see this a lot. You're going to see places where this formula is necessitated a lot. Okay, and of course, we know that that's A squared minus B squared. Okay, just use this formula straight. Just use this formula directly. Okay, so left is equals to, and so when you see that format, you know that is equals to 1 squared minus cosine squared. Okay, and what is that? What is that? Right? And that is 1 minus cosine squared. And of course, we know the other identity, don't we? That other identity, you know so well, right? Sine squared plus cosine squared is equals to 1. Sine squared plus cosine squared equals 1. So sine squared of anything plus cosine squared of anything is equals to 1, right? So now that anything is x, right? That anything is x, right? So this is x, right? So when we have 1 minus cosine squared, sine squared is equals to 1 minus cosine squared. Okay, so this piece equals to sine squared of x. And how far is that from cosecant? How far is that from cosecant? Well, we know that because you're going from left to right, right? So how about we do this? We use the third format. We're gonna use the third format. So the left-hand side, we ended up here. So let's see what we get from the right-hand side, right? The right-hand side, we have 1 over secant squared, right? And what would that be? We know that cosecant is 1 over sine, right? 1 over sine squared, right? And what would that be? And that's going to be 1 over sine squared. If we multiply both top and bottom by that common denominator is sine squared, right? We multiply by 1, anything times 1 stay the same. And we will end up the denominator 1 over sine squared multiply sine squared, that's going to be 1. So the denominator is going to be 1. The numerator 1 times sine squared is sine squared. So in the end, we get sine squared, right? So the right end up with a third place, left end up with the third place. And then what do we say? We say thus, right? This is true. This is true, right? So I can totally just change this to be proof. Okay, change this to proof. All right. Okay, so this is number 1. The next one, as I said earlier, I want to work with you on number 3. Okay, we can do number 2 in a minute. But here I want to demonstrate to you some of the commonly used formula, right? This is 1, right? This is one of the formula which is often used. Okay, and there's another formula which is a plus b squared. Okay, sorry, squared. You're gonna see those, the place of application may show up in different shape and forms, but we need to see that it is in nature. That's the problem. That is what is being asked for. 2ab plus b squared. Oops. Okay. And the next one is a minus b squared. Okay, which is going to be a squared minus 2ab. I know most of you can do FOIL, but you don't have to do FOIL every single time. Okay, you don't have to do FOIL every single time because sometimes it unnecessarily complicated your work. Just use these formula directly. Just use these formula directly. So I'm going to give you a compact form of these formula. Okay, the compact form is to say if a plus b squared is a squared plus 2ab plus b squared. And the next one, right? This is the one. So when this is a plus and that's plus, everything stayed the same. When this is a minus and this is minus and everything stayed the same, right? So these two formula are typically combined into here as plus minus, which represent two formula, meaning when a plus b, here you choose a squared plus 2ab plus b squared. When you have a minus b squared, you have a squared minus 2ab plus b squared in that order, in that correspondence. So you only have to remember two forms, okay? Besides, whenever you're lost, you can always use FOIL to verify and just do the FOIL on the scratch paper. By the time you're in calculus class, even by the time you're taking these classes, right, trig or pre-calculus, you are expected to know these formula very well. You are expected, okay? All right, so let's look at number 3. Number 3, we have sine x plus cosine x squared. And on the other side is 1 plus 2 times sine x cosine x. And once again, to prove. Okay, so we don't know if it's true. We pretend we don't know, right? But we know that what is to be proved. That's the nice thing about it, is we know what is to be proved. Okay. So, okay, so let's try not to write on scratch paper. Maybe we can nail this, right? In moments of need, we will just turn to scratch paper. Left-hand side. Okay. So you imagine this is A and this is a B. Okay, this is A and this is a B, right? So let's do scratch paper then. Think out aloud. Think out aloud. Okay, I'm going to show you the process. This is my A and this is my B. Okay, so my A is sine x. My B is cosine x. Okay, so for A plus B squared, I know it's equals to A squared plus 2AB and plus B squared. Okay, so since I know my A is sine x, so I'm going to bring my sine x in place. So A is replaced by sine x. A is replaced by sine x. Oops. A is replaced by sine x. Right, so everywhere A is replaced. B is cosine x. Okay, so B is a cosine X. Okay, so that's that substitution, right? Okay, so B is replaced by cosine X. So this B is replaced by cosine X as well. You see? And then sine X multiply sine X, we use the shorthand notation, sine square of X plus 2 times sine X cosine X and plus cosine square X. Okay, so that's how the substitution is actually done. You can do this mentally, or you can do it on paper, especially when you're not, well, especially you're still trying to catch up with other courses. Remember, this course is it's just not one course, right? It's 5-6 courses in one, 5-6 courses in one. So on the one hand, you're juggling trigonometry. On the other hand, you're juggling reviewing algebra classes. So this is what you do. This is what you do. And then sine squared plus cosine squared, this makes 1. So we can bring this physically together. You don't have to, right? We can bring them physically together. Or you can just so this step is completely optional. So this step is optional. Okay, and the next, right? Sine squared plus cosine squared, that's 1. So 1 plus 2 times sine X cosine X. So that's proved. That's proof. So from our scratch paper, right? Now show work. Show work. When you show work, you don't need to show that process of I was doing substitution. Okay, so I'm going to show you how you would show work in this case. Okay, this is to be proved, right? This is to be proved. So I start from the left-hand side. My solution, right? Left-hand side. I'll copy the entire left-hand side. Always. Okay. And the next step, actually, I'm skipping this piece. Okay, I'm just going straight to there. I'm going straight there. Okay, I have my equal sign nicely lined up, color coordinated if possible. Okay, and this step can be skipped. Okay, I leave it there. You know, some of you may want to show that, which there's nothing wrong with that. And in the end, you're going to tell the reader, right, that's the right-hand side. Okay, then you say, well, isn't that obvious? The reader can see. Yes, yeah, the reader can see. But in mathematical proof, sometimes it's the best that you pointed out the most obvious and most obviously. Okay, just to make your point. To make your point, you point out the most obvious. Okay, because something may be obvious to you, but it may not be obvious to someone else. When you point it out and bring them together, you're making your point. Okay, then you say thus, right? You always have a closure, for your proof. Okay, sorry. I was just trying to copy and paste, right? All right, sorry. So always have a closure when you prove something, right? So if you present this kind of work to any teacher, you're only going to get all the credit. You're only going to get all credit. There's no other choice. Okay, if you present work like this, you're going to lose half the point. You're going to lose half the point. Depends on the teacher. Depends on the teacher, I would say. Okay? Depends on the teacher. But you are going to lose some point for sure. Okay, if that teacher is following the mathematics, following the convention of the community. So let's do some more. So at this moment, I hope you guys have been following me. Okay, so I will try to do something. I will also try to do something that with a fraction involved. I know that's the weaklings of a lot of our students. It's okay. So when fraction form, anything in fraction form is presented, we could get very confused. Okay, we could get very confused, or some of us. Okay, so let's look at number 2. Number 2 is to prove the 2 fraction form. Okay, cosine x divided by secant x plus sine x. Okay, sine x over cosecant x, and that equals to 1. That's interesting. And very obviously that in this case, most likely we're going to start from the left-hand side. Right? We're going to start from the left-hand side. Okay, so let's see. Well, scratch paper may be necessary. For me, scratch paper is always necessary. I always have scratch paper all over in my office. Okay, always have scratch paper in my office. Okay, all right. Think out aloud. On my left-hand side, I always copy the entire left-hand side. And then I'm looking to the right. I'm looking at the right, I'm looking at the left. Left, right, I keep looking. And I want to develop some kind of strategy so I can get to where I am, right? I get to prove it. All right, so what are we gonna do, right? What are we gonna do in this case? Obviously, denominator is an issue, right? Denominator is an issue. And we can go find the common denominator. That's one way to do it. And the other way is to see, you know, we have secant and cosecant has some relationship, right? Secant is 1 over cosine, 1 over cosine x. And cosecant is 1 over sine x, right? So I will have 2 fractional form. From these 2 fractional form, maybe I will simplify the complex fraction, right? So you look at this fraction and you look at this fraction. And meanwhile, I'm maintaining this equal sign. Remember, even though we have these equal sign, they are there necessarily, but we need to make sure we should not take them for granted. Okay. In the sense that you have to constantly justify your next expression is the same as the previous. So now what I'm going to do is that I'm going to multiply the common denominator of this complex fraction, which is a cosine x. Cosine x. Okay, for this other one, I'll be doing the same. Sine x multiply sine x. Okay, so now you can see some simplification, right? 1 over cosine x multiply cosine x. Some of you may like to see it that way. Same thing, really. But if you want to see it that way, do it, okay? If you want to see it that way, do it. But you can see that makes 1, right? And that makes 1. And what do we get on the top? Cosine x multiply cosine x. That's cosine square of of x. So we got a square here. And over here, the same thing, the same story, cosine squared. Okay. And could I remove the denominator? Of course you can, right? But this is on scratch paper. So, and I got a cosine squared plus sine squared x. And that equals to 1. And that is our right-hand side. That is our right-hand side. Okay. So we got it. So let's see how we show work. I'm going to give you a version of work. You really don't have to show everything you do on the scratch paper. Okay. You're not going to impress more or impress less if you show the adequate steps. Okay. So oftentimes students ask me, how much work do you want me to show? You know, this is a very difficult question. This is a very difficult question, but it's a classic question. It's a classic question, right? So how much work should I show? I would say adequate amount of work, adequate amount of work. Okay. For example, in here, right? In this play, in this process, I could have removed this step completely and nothing will be taken off from my work. Okay. I can even take off this piece. I can even take off this piece. Okay. So, I put it optional because I know that some of us may need it. Okay, optional. Okay, the work I just deleted can also be optional. I can totally see some people doing it. Okay, so this piece is also optional. Optional means that when you show these pieces of work, if you show them correctly, you're not going to lose any point, but you're not going to get more points either. That's what I meant. If you want to show these work, if I were you, I would not show these work. I would just go just 1, 2, 3, three steps, it's done. Will I get all the points? Most likely, yes. Or of course, you say, you're not going to grade your own work. Of yes. I've been student before. I was student before, right? You guys understand that. I was student for many years, right? So I can only tell you for that question that how much work I need to show, adequate amount of work, adequate amount of work. But what is adequate amount of work, right? It varies from question to question. So I will never be able to tell you, oh, you need to show 3 steps, or you need to show 5 steps, or you need to show 10 steps. But some question like this, no matter how hard you work, you're not going to make it 10 steps, right? So it's just an adequate amount of work, adequate amount of work. So for me, both steps are optional. But if you find it necessary to show it by no means, but make sure you show it correctly. You show it correctly. If you don't show correctly, you may lose point because of it. Let me say it again. If you don't show work correctly, right? Sometimes you show a little too much, which is not necessary, but it's fine. You show too much is okay. But you have to show, you have to make sure everything you show is correctly justified. I hope I made myself clear. Okay. All right. So thus it's proved. You see, we always have a closure. Always have a closure. Okay. This is the question to be proved. And I start from the left and ended up on the right. Therefore, it is true. So that is a logical flow of working with this kind of question. Okay. So let's look at, let's see what else. I think number 4 might get you interested in. Okay, number 4. Okay, number 4. Number 4, we have cosecant x minus sine x equals to cosine x multiply cotangent x. And of course, we are to prove it. We are going to prove it. Okay. Even though there's no obvious numerator denominator, but I can see there will be. There will be. Okay, there will be. So I will put, I think I will start working on my scratch paper. Okay, my left-hand side. I start from the left. You could start on the right, okay? Don't get me wrong. Okay, you can. So I start on the left, and it looks like there's nothing I can do on the left, right? Unless I do something to you know, to make something happen. So I'm going to write it's equal sine x, right? Cosecant equals to 1 over sine x. So this is multiply sine x. Now we need to make common denominator. So we're going to make common denominator. The common denominator is sine. So we're going to multiply 1. And that 1 is going to serve our purpose to get that common denominator. So sine x under sine x. Okay, so as a result, what do we get? We have the same denominator, which is sine x. We're going to keep it. Okay, on the top, we get 1 minus sine square x. And now I have the top. What is on the top? The top is cosine square x. Whoops. And the bottom is sine x, right? On the one hand, we can go this way. We can just go one more step. Or on the other hand, I can do the third format, right? I can do the third format. Yes? Right, so it's optional, because if you can do one format, you can do another format. Okay, you can do all 3 format. In fact, for every question, you can do all 3 format. Okay, so I'm going to do in the first format. Okay, so I have cosine x. I'm going to break up cosine x squared into cosine x times cosine x. So cosine x, right? We got a cosine x. And cosine x divided by sine x, that's a cotangent x, right? So then you get to the right, But you can also use the third format. And to keep it simple, I already got it, okay? I already got it. So that's the right-hand side. I'm done, okay? You can do the third format, totally. I'm gonna leave that for you. Okay, so let's see how much work we're gonna show. Right. For the same question, how much work I'm gonna show. So I'm gonna copy and paste. And think out loud now becomes the solution or proof, right? So I start from the left, right? And I go this way. This way, right? So I'm almost done. So which part can be omitted? Is there any step I can omit? You actually could skip this one. This step you can skip. You can skip that one. You can skip that one if you wish. Right? You can even skip this one. You can even skip that one, but you just have to make sure everything is done properly. Okay, all the equal signs are justified. Sometimes you skip one step and the teacher has to work out that steps that's omitted to justify it. So I think this is fine. This is fine. Okay, one less or two less or one more, two more makes no difference. So you say thus proved, right? So you can see that's the body of work. You can have one step more, two step more, one step less, two step less. That's not going to make a major difference, but every equal sign has to be justified. So you're telling the reader, the left is this, right? And this piece is the same as the next piece. So every letter piece is the same as the previous. That's the narrative. That's the narrative, right? This is the same as before. This is the same as before. And this step is the same as before, and so on and so forth. And in the end, the left ended up to be the same as the right. Okay, I hope this helps. Let's try. I think you guys can do number 5, no problem. I'm going to work on number 6 with you. Okay, this is going to get into somewhat somewhat maybe complicated expressions, but no fear, I'm here. Okay, cosecant x divided by tangent x plus cotangent x. And we want to prove that the left-hand side is the same as the right-hand side. So this is to be proved. So now we're going to make believe we're going to be in that pretend, right? Pretend this is not true. We don't know it's true. Pretend we don't know it's true. By the way, excuse me, this pretension is not necessarily, unreasonable, because sometimes there are mistakes. There are mistakes, okay? I make mistakes, other people make mistakes, textbook makes mistakes. So, to be proved it's actually, it's not too much to ask for. Okay, so I think we definitively will start from left. Definitively, we will start from left. Okay, because if you start from right, you don't know, even though you know where to go, but you still have to figure out what I'm going to, you're going to make it more complicated, right? Make simple is easier. Make more complicated, maybe a little bit harder. It takes a little bit more imagination. Okay. All right, so we start from the left. You can see sometimes I write horizontally, sometimes I write vertically. Depends on the space. And on this one, I'm going to write it vertically. And now, one by one, and in this current situation, there's not much we can do, right? So we're going to have to convert them. So secant is going to be 1 over cosine x. Cosecant is 1 over sine. The denominator tangent is sine x over cosine x, and cotangent is cosine x over sine x. We get into a complex fraction. All right, so let's see, what do we do next? And needless to say, we're going to find common denominator, right? Common denominator. So what is the common denominator? Right? So on your scratch paper, you're going to scratch some more. And then we agree right? The common denominator is going to be this denominator, this denominator, this denominator, this denominator, 4 denominators considered. And we realize our LCD, right, is it going to be what? Is it going to be sine X multiply cosine X? Okay, you may like to pause here to work it out, your steps, and then come back to watch my recording. So hopefully you're back with, if you paused, right? We're gonna multiply the common denominator. Okay, how we're gonna do this? Okay, I'm gonna show you in a sequence of steps. You multiply by 1. We multiply by 1, so that justifies the equal sign. That justifies the equal sign. But I'm going to take this number to multiply the 2 terms on the numerator. So I'm going to take this piece, multiply with the first, second, okay? And the dot is not necessary, but if you like to see it, sure. And sometimes people like to see it this way. It really makes no difference. It makes no difference. If you like to see it this way, show it that way, or do it yourself that way, okay? And I'm going to take this piece and do the same thing. Multiply, okay? Multiply there. And that's the process. That's the process. Okay, so take a close look. If you need this much detail, it's great. You just have to make sure you work out every single details. Okay, so now I'm going to work out the details. I'm going to work out the details. Oops, what did I do? I just want to copy and paste there. Okay, I duplicate it, so I'm going to keep the one on the top, and I'll be doing the simplifying here. You can see cosine, and this cosine will be reduced. So this entire piece, we only have sine left. So this piece, we only have sine left. Okay, and this sine and that sine is gone, makes 1. So cosine X is left for this entire piece. In the denominator, right? So cosine and cosine are reduced. So we have sine times sine. Sine times sine is sine squared. So sine squared of X. And for the other side, sine and sine is reduced. So we have cosine times cosine. So this entire piece, we have cosine squared X left. Okay. That's exciting. That looks exciting, isn't it? Because the denominator is 1. Denominator is 1. Right? Sine squared plus cosine squared, that equals to 1. And of course, we're left with sine X plus cosine X. Is that what's on the right? Yes, nice. So we reached the right-hand side. We reached the right-hand side. Okay. We reached the right-hand side. And then we can put it and organize the work and show work, right? So let's show work. Okay, let's show work. So we are to prove that, right? And for me, I just copy and paste. Okay, so think out aloud is no longer necessary. right? So it's just going to be my solution. My solution, I start from the left, right? I wrote down this way, and then multiply, right? Multiply every term by the common denominator. And we get to this point. I would say this step is optional. Okay, but you should not stop here. Okay, if you get here, you should always go here. All right, because one denominator equals to 1, it can be written down even more simply. Okay, so then you say thus, as always, okay, you bring the question to a closure, closed. That's the closure, that's the closure. Okay, that's the closure. So that's number 6. You can see some of these questions seem to have some rhythm, right? Seem to have some rhythm. Excuse me. Shall we try number 8? I think you guys can handle number 7. Okay, let's try number 8. Number 8, on both sides seem to be complicated, right? So I'm even thinking maybe we need to do the format 3. Okay, let's see if we need to do that. Okay, so before we start, do you think I have the magic bullet? Do I see the steps? I probably can see a couple of steps, but I couldn't see all the steps until I write it down. Okay. I'm not such a genius that I can see through, right? No, I cannot. I have to write it down. When doing math, I always have to have scratch paper with me. Okay, if you come to my office, you're gonna see the scratch paper is everywhere. It's everywhere. Maybe think out aloud. Think out aloud. So my scratch paper. Okay, that's my scratch paper. I can should I start from left to right, right to left? What should I do? Well, let's do something. Okay, so I'm gonna start from left, as always. Right. There's certain certain thing we can say about habit, right? Most people start from the left, but doesn't mean you should not start from the right. Okay. All right, so if I start from the left and I look at the right, and I think the right thing to do will be rewrite tangent as sine over cosine. So I'm rewriting tangent as sine over cosine. Okay, so this may bring us closer, right? Bring us closer to sine x over cosine x. And what do we do next? There's a common denominator, cosine x, right? There's a common denominator. So what I would do is that I'm going to copy the whole thing, and I know I'm going to reduce the complex fraction, right? So I'm going to multiply cosine x over cosine x. This is 1, okay? This is 1. Cosine x over cosine x. This is 1. Okay? If you write only cosine x, this is no longer 1. If a number that's not 1 multiply the same quantity, that this equal sign would not be justified. So if you write it this way, you're going to lose point. So don't write it this way. you have to write that 1. In other words, you have to write cosine over cosine. You have to write cosine twice. Okay, excuse me. You have to write cosine x twice to guarantee that you're multiplying this expression by 1. Anything times 1 stay the same using principle number 1. Okay, that's very, very important. Very, very important. Now, how do we use it? Right? We can use it on the next step. Well, this is on scratch paper anyway. On my scratch paper, I try to show everything as clearly as possible. Okay, as details as possible. So not showing everything as much as possible, but showing as much details as possible. Details. Okay, you can show all the detail. You can see when you show your work, sometimes you can trim this, trim that, right? But when you show work on your scratch paper, I actually will show as much detail as possible. Why? Because it's easier for me to come back to check. If it doesn't work out or something was wrong, I can go back to my scratch paper to check. If I already have the details in place, it's much easier to check and it could save you time. But anyway, so next I'm going to take this cosine and multiply each term with it. Multiply, okay, multiply, and I'm taking this piece and multiply and multiply there, right? So this is being applied. If you want to write it this way, you don't need to. You don't need to, okay? But if you do, no problem, no problem, no problem at all. So cosine x times 1, that's cosine x. Cosine x times 1, that's cosine x. So here, cosine x reduce. So we only have sine x left. And over here, cosine and cosine reduce. So you get sine x. That's the right-hand side. We're done. You see, at the beginning, we were thinking maybe I need to do left and then do right and let them meet at the third place. Now we already got there. All right. Wonderful. So here we go. We got the right-hand side. It's easier than we thought, right? It's easier than we thought before we start. So once you put your work, once you put it, you make that effort, it's not as hard as you thought, right? So there we go. Let's show work. Oh boy, I need that drink. Excuse me. All right. Show work. Okay, show work for what? For this piece. Okay, how do I show work? Okay, this is to be proved. And that's my solution. Right? And I got, there any steps I can trim? I will tell you this step is maybe optional. Okay, this step is optional. But it's up to you. Okay, to me, it's nice to show. Okay, what you can trim these. You can trim these. And you can trim the divided by 1. So for example, you can just write cosine x. Okay, because you don't need to do that. You could do this. I'm saying you could. If you leave it as it was before, that's fine too. Okay, and then you can say thus left equals to right, left equals to right. It's done. See, it's not as difficult as we thought. Okay, it's not as hard as we thought. So I'm leaving 7 to you. How about number 9? Number 9 is interesting, isn't it? Number 9 related to, let's try that. Let's try that. Number 9. Okay. Number 9, we are to prove. We're going to prove something. There's something. Did you notice that there's certain rhythm, right? In the way these questions are made. Okay, 1 over secant x minus tangent x, and that equals to 2 times secant x. Interesting. How could that be? So first, I usually make sure I copy the question correctly. Is it possible that I put down the wrong question? Yes, that is possible. That is possible. If you suspect of that, please let me know, okay? Because I always give myself some space, right? For selfish reason. I could make mistakes. Okay, on the other hand, I have the chance of my mistake is not 100%. It's usually less than 50%. But anyway, without further ado, most of the time it's correct. Most of the time it's correct, but it's not correct until we proved it, right? It's not correct until we proved it. So I double check if I copy the question correctly. Okay, so scratch paper again. Think out aloud. Okay, that's my scratch paper. And of course, we start from the left. Okay, we start from the left. We have different denominators. Okay, we have different denominators. So what do? We have to make them the same, right? We have to make them the same. And the denominators are interesting. It looks like there are conjugates, right? There are conjugates, aren't they? They're conjugates. A plus B times A plus B, A minus B. Do you see that? You guys see that? Okay, we have in the denominator. Okay, this is just a note for myself, okay, or my mental note. Denominator, right? There are conjugates. So A plus B and A minus B. Just a thought. There's nothing we can do. Nothing we can do at the moment, but I take a mental notice. Okay, for that denominator. They're not the same for sure. And what is the common denominator? The common denominator, obviously, is A plus B multiply A minus B, right? Is this denominator multiply the other denominator? Okay, so I recognize the common denominator. The common denominator, okay, so I'm going to put it as LCD. My LCD is this piece multiply that piece, A plus B times A minus B. Do you guys follow me? And what is more, A plus B times A minus B is A squared minus B squared. So we have A, this is A, and that's B, right? So that's going to be secant squared of x minus tangent squared of x. So my common denominator actually has two forms, I can use either one. So now I'm going to make that common denominator. So I'm going to copy and paste my original expression. Okay. And I'm going to make the same denominator. The same denominator, we know the common denominator, right? In the first denominator, we have the secant plus tangent. So what's missing? We need a secant minus tangent. And we need to do the same for the top because we want to maintain that equal sign. So anything times 1 stay the same. Okay, so let me make the fonts just a little bit larger. Okay. So I push that on the side. So the first piece is taken care of. Now we have the same denominator. The second piece, right? We have secant x minus tangent x. So what's missing is secant x plus tangent x to make that common denominator. But to balance the equal sign, we have to multiply that number on the top. So this is anything times 1 stay the same. Principle number 1 is used all the time, very, very often. Okay, very, very often. Okay. So now we're reaching the next step. On the next step, right? On the next step, what do we have? Okay, what do we have? Of course, we already have the common denominator, right? Secant x multiply tangent x, right? So we have the common denominator already, right here, for both, right? For both. That's nice, isn't it? And the numerator, secant x minus tangent x times 1 is just going to be secant x minus tangent x. 1 times secant x plus tangent x is going to be secant x plus tangent x. Anything times 1 stay the same, right? And then what? The next step, we're going to combine the numerator because we already have the common denominator. So we're going to take the numerator and this numerator add the other numerator. So this piece, okay, we're going to add to the numerator on the first one. So this piece is gone. Simplifying. Okay. Right now we're focusing on the top. Okay. The numerator, secant x minus tangent x plus secant x minus tangent x, look like there's a negative tangent x and there's a plus tangent x. And these two are opposite, so that makes 0. And secant x plus secant x, we get what? 2 times. We are so close to it. We're so close to you see, we already got to we already have the right side on the top. So if this statement is true, the denominator must be 1, isn't it? But is the denominator 1? The denominator is the same as the common denominator. And of course, it's also the same as secant squared plus tangent squared. So I could replace that now. And I could even replace that earlier, don't you think? Because they're the same. You can write one or write the other, right? They're the same thing. But what is secant squared minus tangent squared? What is secant squared minus tangent squared? Huh? Well, for this, you kind of guessing it should be 1, but you have to justify it, isn't it? You have to justify it. So how do you justify it? How do you justify it? Right? So now we guess, right? This is going to be equals to 1. But is it equals to 1? Is it equals to 1, right? So we put a question mark. Is there a formula you remember from past that will give you that adjustment? give you that rationale. Okay. If you remember a certain formula, okay, I will talk about what if you don't remember, right? That's not the end of the world. If you don't remember, that's not the end of the world. If you remember this formula, when we started with sine squared, right, plus cosine squared, that equals to 1. Everybody knows that, right? And if you, this is true, right? This is true. From this truth, we are going to, oh, oops, right? We're going to take that, right? Whoops, what am I doing? Okay, so from this truth, right, we can divide both sides, every term by cosine squared x. Okay, so we're going to divide by the same quantity on every term. If we do that, what do we get? We get tangent square x plus 1 equals to secant square x. Right? So now we have a secant square minus tangent square. So if you, some of you might remember this formula. If you remember this formula, is even better. But it's, if you don't, it's not big deal, right? So from, if you don't, you remember you just remember this very basic identity, you can still derive it. Right? If you just have the will to derive. So from here, from this truth, if I subtract tangent square x on both sides, and I will get 1 equals to secant square of x minus tangent square of x. And there we go, right? So you can see secant square x minus tangent square x is directly derived from sine square plus cosine square equals to 1. So at this point, you can just say that equals to 1, right? 2 times secant x divided by 1. Okay, you certainly can tell the reader that you know this formula. Okay, you can tell the reader, hey, I know this formula, or you derive this formula. Okay, and it's proved. It's proved 2 times, of course, 2 times. Right? So we can see along the way, because we know the left and we also know the right, we know we're trying to prove left is the same as right. So we have a direction to go when we prove these identities. That's the nice part about it. So you know where you're going. So with all these said and done, let's put the proof together. Let's put this proof together. Show work. Okay. When we show work, we always start from something. We never start with the thing we are to prove, because we pretend we don't know that's true or not, right? The ER proof, of course, we're gonna trim. We're gonna do some trimming. Okay, we're gonna do some trimming. So I'm gonna put solution, right, the left-hand side. You don't need to tell the reader about that. Okay, you don't need to. And whoever grades your work, people who grade your work, we can tell. We can tell from your work. Okay. And do you need to show that? Optional. I would say this piece of showing is actually optional. Optional to show. If you show, you better be right. That's my point. If you show, it better be right. Okay, because anything and everything you show will be judged. Your work will be judged. Okay, so if you show, it better be right. If you show a wrong work, even though it's optional, you still lose points. You still lose points. Okay, so now with that said and done, we have these common denominator demonstrated. And I would say this step is actually optional. Because it will be reflected on your next step. Okay, so optional. So you can go from here straight there. Yes, you can. Okay. And you show this work. And then what? And then what? On this piece, you actually could already apply this property. So you can put it here. Okay. This piece will be nice to show. This piece will be nice to show. And what if you don't remember? Do you need to do you need to show that you derive it? No, you don't need to see. You don't need to show how you derive it, because in most of the context, it depends on your teacher. Really, depends on your teacher, right? If this been taught, in our case, we have taught this, right? We've taught this in deriving identity, deriving formula, right? Deriving, the formulae part. We have done it. So if it's this been taught, you don't have to show it again. So that's all. That's all. And then of course you're going to tell the reader, hey, I reached the right-hand side. I have just reached the right-hand side. And then you can say thus, right? Thus, it's proved. Thus, it's proved. Okay, so that was number 9. That was number 9. Okay, that was number 9. Okay, so the last one, we're going to do the last one, number 10. Number 10, we might think of start from the right-hand side. We have start from the left-hand side most of the time, right? So how about we start from the left-hand side this time, right? And we don't know which format now, right? Because sometimes we anticipate we might need to use a format 3. We ended up get it by format 1. So let's keep our mind open, especially when we write on scratch paper. Really, keep our mind open. Sometimes you think it's a complicated, and some other time you realize, oh, it's a simpler than I thought. Minus cotangent x. Okay, so we got this to be proved. We got this to be proved. Okay, so think out loud. How about think out loud? Okay, I always feel comfortable to work out some steps on my scratch paper. Okay, and you said it's a habit, or it's just to be on the safe side. Okay, to be on the safe side. Okay, let me make sure we copy the question correctly. Cosine x over 1 minus sine x. On the other side is sine x minus cosecant x, cosine x minus cotangent x. All right. So this time we start from the right. Start from the right. We start from the right. Okay. Nothing we can do. Nothing we can do. And then we look the left. We look at the left, right? In the left, there's sine, cosine. So naturally, we're going to do some conversions. Okay, we're going to do some conversions. Cosecant x, that's 1 over sine x. 1 over sine x. We have a cosine x here, and cotangent x is a cosine x over sine x. Right? Cosine x over sine x. We have a common denominator. And what is that common denominator? Sine x, right? So we're going to multiply that common denominator, sine x over sine x. You must write it twice. You must write it twice. If you write it once, I will catch it and you may lose points because anything times 1 stay the same. We didn't learn that anything times anything stay the same, right? So you have to use it. You have to know your principle. You know your principle. So I'm taking this sign, right? So I multiply by 1. Since this is on my scratch paper, I can just take this number, multiply that, and multiply that. And take this number, right? Multiply with sine, multiply it with each term. So this piece is gone. Don't need it. Don't need it. Simplify. Simplify. What do I get? What do I get? Okay, you also keep an eye on your left-hand side. Okay, because we start from the right, we're reaching to the left. Right, so this piece is 1. And this piece is cosine x. Okay. Sine x times sine x, that's sine square x, isn't it? Cosine x. And this top has, the top remind me of something. The top remind me of something. What is that something? What is that something it reminds you of? What is that something it reminds you of? Yes, it probably reminds us of sine square x plus cosine square x. Whoops, that x has to come down. Whoops, cosine x equals to 1. So sine square x minus 1. So if I bring the 1 to the left-hand side, I will get sine square x minus 1. That's going to equals to negative cosine square x. So the top can be replaced. And what about the bottom? What about the bottom? So this piece now is negative cosine x. Negative cosine x. That's interesting, isn't it? On the left-hand side, there's a cosine alone on the top. So you may think of reducing, right? So what do we do in the denominator here? We can factor, can we? So cosine x times sine x minus cosine x. So if we factored out the cosine, right? So we get the factored form. We get the factored form. And so cosine x is going to take away that cosine x, one of the cosine x, because cosine x squared, okay, be careful about the sign, okay? Cosine x squared is equals to cosine x times cosine x. Okay, so now this cosine x will take away one of the cosine x on the top. We're closer to the left, aren't we? We're closer to the left. But the negative sign is on the top. So how about I bring the negative sign to the bottom? I bring the negative sign to the bottom. Same thing, right? Now the top is matched. The bottom, I'm going to apply the negative sign inside. So I have negative sine x plus 1. And isn't that the same as cosine x over 1 minus sine x. And did I get the left? Yes, we got it. We got it. And that's the right-hand side. I'm sorry, that's the left-hand side. Excuse me. Okay, so that's the left-hand side. We got it. We got it. But pay attention to the sign manipulation, right? Because here we have that deriving, so be careful. Don't drop the sign. If you drop the sign, you won't get it. You won't get it. So each step, the sign manipulation is very important. Don't drop a sign. You be very, very careful, in other words. So we got it. Okay, so now let's put these together. Let's put these together. Okay, so we're gonna do some trimming. Okay, we're gonna do some trimming, and I'm going to show the proof. Right. So how much work you're gonna show, and we don't need to think out aloud anymore. So solution. We start from the right. We start from the right. Okay. So what are the steps I could trim? Right. I would say this step is optional. Optional. If you go from here straight there, even straight here, it's fine. Okay. So on these two steps, just show one of them, it's fine. And the next one, you must show this piece, because if you miss this piece, you might be in trouble. You might be in trouble. I would say that step is optional. Okay, this piece is optional. Okay, which you write a cosine square as a cosine times cosine, that's optional. Okay, and the next one, you could actually go from here directly there. So this is optional. Okay, so this piece is optional. I mean, that piece. Okay, you can go from here directly there. Showing a little more work is helpful. Okay, so the optional I put there is just for the thought. If you find it necessary, just put them there by all means. Once again, you can show more, you can show less. It's your judgment call to show the adequate steps. Thus, it is true. There we go. We proved it. Right. This last one was interesting because we finally get a necessary chance to show from right to left. Most of the cases you do, but be open-minded when you work on your scratch paper, right? And once you put it to your pen, okay, you start writing it down, you will get better day by day, hour by hour. So don't just watch. Every time you watch, make sure you have paper pencil with you, whether it's virtual or on paper. I'm just old-fashioned. I use paper. I'm not buying new paper, by the way. I know we're conscientious about going green paperless. There's just so much paper still laying around. I haven't bought any new paper for years, but there's still so much paper laying around. So if you're like me, you don't want to buy more new paper, but just find some used paper, some paper that's not being used, and that will be enough for you to do math. Okay. But anyway, without further ado, and I wish you a very nice day, and thank you for watching. Until next time.